Oh, there we go.
Go.
Do you think we're gonna be able to go?
I think it's starting to show.
We have 20 minutes.
That was awesome.
Pretty short, so okay.
Hey, how many know that inside wings like down the
Wait, can I?
You didn't finish the
Alright, go. Who's that? So the next one
Get our thing up,
is
because we have a ton of stuff.
Can you stop doing that?
introduce the group.
Oh, we're Martian
You want me to
basketball,
roll it?
also known as chicken McNuggets.
Where does this like snake?
Just pull it
It's like
down.
curtain.
Oh, I think that's the official name for it.
Martian
Okay.
Yeah, Martian basketball.
And the official name is Chicken.
Chicken McNuggets, sometimes called coin dog. It depends what you're looking at. How you look at it.
A little mouth.
Oh, it's okay. So most of ours we have in a presentation. Do we have one of those stick things? Cary, you have to.
Oh, yep.
Are you gonna click? Here, Nick, can you click and then Cary can run? When do I click? All right. So this was our question, which was what scores cannot be attained if there are two ways of scoring in a particular game of Martian basketball, and this is one way and this is another. You can also say it's just linear combinations of A and B, where A and B are natural numbers. Click. So we had a couple objectives we wanted to do.
Okay, so I wanted to generate the number of unattainables for any given A and B.
And by unattainables, we mean any scores that you can't obtain by making some linear combination of A and B.
And generate the highest unattainable for any A and B. Find all possible pairs A and B for a given number of unattainables. And find all possible pairs A and B for a given highest unattainable.
Basically, we were looking for scores of which scores you can obtain, patterns of which scores you can obtain and which you can't. Click.
Are we good, guys? Everybody got the idea? Yep. Okay.
So the first thing we started doing was looking for some data because we really had no idea what we were looking for. So we made a chart. Zoom? Yeah. Well, we have a better chart. This is our first chart. So we made a chart of A and B's where A was less than B just for the sake of being evens. And then we looked at all the scores you couldn't get manually. And the first thing we realized that for a certain A and B's, couldn't get an infinite number of scores, and those were when A and B weren't relatively prime, because that we knew immediately that any score had to be a multiple of the greatest common factor of A and B. Right. So instead of looking at the number of the actual scores themselves, we just looked at the number of unobtainables, as we call them, and we noticed a lot of patterns. Cary, why don't you talk about the patterns you noticed?
Well, starting
A little mouth.
triangular numbers on this diagram.
What do they mean?
Like this. So along this diagonal here, there are triangular numbers, like 1, 3, 6, 10, 15, and so on. And then
What do they mean? What are they doing there? What's the meaning of it?
I don't think they have a meaning right now.
Just when A and B were a particular thing, and then we define that later.
Okay.
And then there are square numbers along this diagonal, 1, 4, 9, 16, 25, and so on. And then, okay, well, some of these numbers are missing because A and B are relatively prime, but we still notice that these are pentagonal numbers along here.
What are pentagonal numbers?
Here, I'll draw pictures.
We looked at the geometric definition of it, and that's initially how we hoped to solve this, but you can basically arrange the numbers into a pentagon that fits inside another pentagon, just like triangular numbers.
So the first pentagonal number would be, for example, 1.
1.
And the next pentagonal number would be
5.
5. And the next pentagonal number would be how many ropes you need to add.
And then so the more you keep moving this, there's hexagonal numbers along there. And then, yeah, you can get any
Like, this is the other.
This is the other chart. for height.
Since one of our original questions was also not only how many numbers you can't get, but what's the highest number you can't get, because we proved, as we'll show later, that there is a finite highest score that you can't get. We also looked at this, which was the highest unattainable for doing A and B, and that's mostly Cary's. So these were the two patterns that we noticed, and that's basically what Cary described. Go ahead.
But okay, so how patterns and observations be formulas. So for the number of unattainables, the first thing that we noticed was that when A equals 1, the number of unattainables is 0 and it stays constant, since when you have 1, you can add 1 to any number and get all other numbers.
You guys agree?
Yeah.
And the second thing we noticed is when A is 2, the number of unattainables is B minus 1 over 2. So for the first, when A equals 2, we noticed when making our chart or spreadsheet that it goes in the second row so that for every single
We don't need to recreate the chart, we can just go back to that other slide.
Cary, I think you did that wrong.
Cary,
Yeah.
you did it wrong because it needs to be relatively
Go
far.
back
Yeah.
one more.
So
That's what
it's,
the
yeah,
exercise
you just
for.
need to do
Okay,
two
this
exercises.
was the original thing, so you can just work
Okay, so 1, 2, 3, 4, 5. It keeps going. For A minus 1, 2. And we go back. And the third thing is that for a constant B, the number of unattainables is increased by a constant amount as A increases. So we can go back.
We're just gonna stay on the other slide.
Okay, so like for when B equals 7, it goes up by its constant amount, 0 to 3, 3, plus 3, plus 3, plus 3, plus 3. And it's the same for whenever B is constant, it always goes up by a certain amount as A goes up.
So the way we looked at this and proved it also, which is basically what you're saying, is that first we found the link between any number in a column in A, and then we looked at how it went across and the increase. And you notice that each of those were directly related to A and B. So we were eventually able to come up with a formula, which was A minus 1 times B minus 1 over 2.
And we got B minus 1 over 2 because the amount that it increases by every time is B minus 1 over 2. 11 minus 1 over 5. It increases by 5 every single time. And it's A minus 1 because the first column, when A equals 1, it's all 0 because you can add 1 to get all other values. But so the first row, we ignored the first row, first column because
We didn't really ignore it, it fit into our formula also, obviously. A is 1, then B minus 1 is 0, so the times in 0.
and that's what we got. So we still has for a number of
Can you
unattainables.
click ahead?
That's what-
So after we, next one.
Okay.
So yes, that was our next question. So we had figured out how we can take the A and B and get the number of unobtainables. So now we wanted to see if we could go the reverse and we could find A and B's that work if we're given the number of unobtainables. So go to the next slide. So we looked at it like this. So here's our formula. A minus 1 times B minus 1 over 2 is equal to n. And that's our number of unobtainables. But instead, we multiply both sides by 2, so now you have this equation, A minus 1 times B minus 1 equals 2n. And really what this is saying is that there's some numbers A and B that when you subtract 1 from each of them, they're factors of 2n. And we did prove that for 2n, any two A and B that work in this equation, the factors of it, because, I'll show you how we did that later. But anyway, so if you look at factors of 2n, you take any factor pair, subtract one from each of the numbers in the pair, and then you have an A and B that works. And we're able to do the same thing for the highest unobtainable. We can speak about how we got the highest. Okay.
Nick, want to go back 2 slides? Yeah. Okay, so highest unobtainable, we found the formula for this one second. So we basically already had a basic idea of what we were looking for to find the formula from the finding formula of the number of unattainables. So first thing we noticed, again, as the same as in the number of unattainables, when A equals 1, the highest unattainable is 0, since 1 can get all natural numbers. And then the second thing we wanted to find was what is the highest unattainable when A is 2, which is B minus 2. And we want to go to spreadsheet. So when A equals 2, the highest unattainable is B minus 2, 3, 1, 5, 3, 7, 5. And then the next thing we noticed was how much is going up by every single, the constant amount is going up by for a constant B. So it goes up by B minus 1 every single time. So after you get to the B minus 1, B minus 2 for the first column, here, the first column. And then after that, it goes up by a constant amount of B minus 1 for every single A increase. So for 12, 13, 11 to 23 is 12, that's 13 minus 1. 23 to 35, 12, 35, 47, 12. It goes up by a constant amount every single time. And that constant amount is B minus 1. And then to get our formula, we looked at what the constant amount goes up by, which is the constant amount that it goes up by is B minus 1. And then this amount that you multiply that by is A minus 2, since the second column is B minus 2 every time, that's a constant. And so you start the A off from skipping the first 2 columns.
And that looks a lot like our other formula for the number of unobtainables, and we were able to link that later. That wasn't initially what we noticed, but if you expand A minus 1 to B minus 1 over 2, it comes out to AB minus A minus B plus 1, which is remarkably similar to our formula for this, which was AB minus A minus B.
You wrote that?
Wait, it's,
You write that thing really?
Our formula for this was for the number of unobtainables for a given A and B is A minus 1, B minus 1 over 2, which is so that's how we expanded to, and our formula for the highest unobtainable in Cary we showed was AB minus A minus B, and that differed by only 1 and then divided by 2. And we realized later that that was kind of obvious when we looked at it, because if you look at the highest unobtainable, if you add 1, then that just corrects for because it's off by 1 because of the first row. But then because A and B sometimes aren't relatively prime, every other one is going to be an unobtainable. So you can directly relate this to this. And anyway, I'm sorry?
Why every other one would be unobtainable? Why every other one?
Why every other one? Because every other one is even and even numbers.
no,
Wait, what?
but what if A and B are both odd? Then it doesn't make sense. They can be both odd, like A can be 3 and B can be 5, and then that explanation doesn't make sense if they're both odd.
what we're talking. Gopher is the
They're
greatest
not
one
talking about
factor.
AMD.
Actually,
No,
I think it's.
I don't think we're
it's
talking
because-
about the same thing.
No, I think it's because, for each column of these, the relatively prime ones occur at same distance apart. So, yeah, no.
I'm not really sure what you're asking, so I'm gonna skip your question and go to something else.
Okay, yeah.
Wait,
Okay, anyway, let's go back to.
right, there's some, yeah, if you look at 4 and 6,
Yes.
you say 14 is the highest unattainable.
4, 6. Yes.
It seems to me that you can't get any odd number.
No, that's probably not true. Anyway, we made this all last night. Anyway, so what we, our second question, back to what we were talking about before.
Let's just implies we keep,
No, yeah, for some of your unattainables, it's off because
Yeah,
for 4,
this shouldn't, this is.
yeah, that chart's kind of
I'm
funky.
looking at Cary here.
That's right.
Anyway, back to the second half of our question, which was how can we recover the A and B from our formula? So can you go forward? Yes, this. Anyway, so here's our formula: AB minus A minus B, whether or not it makes sense. If you add 1 to each, then like I said here, you can factor it back into A minus 1, B minus 1, and then again, you're just looking for factors of H plus 1. And in a very similar manner, we were able to show that any A and B that work as factors for this have to work in our spreadsheet. So now we have all 4 formulas without actually any hard proofs. Can you go to the next slide, please? Yes. So these were our 4 formulas that we had, and we didn't actually have any proofs for anything at this point. And we still don't have a lot of proofs. But that's a different problem. Can you click again?
You should be able to find the proofs,
Yes.
because just like the previous group, you do have some nice measures.
Yes, we do have. First thing we were able to show quite obviously was that 2 implies 4. That is, given the formula for the highest unattainable, you can figure out which factors work in the same way that they show. And then we also saw that this implies that, which was the thing that you were questioning, but it works anyway. So the highest unattainable implies the number of unattainables because they're related by algebra, and then 1 implies 3, obviously. And 1 implies 3.
I would say we'll have to come back to you guys. You're not done, so.
Jonathan, compound it.
D minor.
Hey, I want one for something.
Oh wait, no, we shouldn't do it.
Okay, so go.
Can I put out a sparring?
Oh my god.